Hello there. In this video, we're going to talk about process-based routing in the Ciw Python package. So the idea here is that maybe you want to predefine or define ahead of time where the customers will go in a network. And just to show a very simple example, we're going to look at a repeating route where actually customers will cycle through exactly the same decision over and over again. So first, let's just go through the code. So we've got import Ciw, of course, and we have to define this routing function. It doesn't have to be called repeating route. That's just what we called this particular one, but it does need to be a function that has this type signature for its parameters of an individual that is going to be some kind of Ciw individual type, and also the simulation itself, and return a list of integers where the integers are indexing the nodes in the network. Okay, so as you've probably seen many times, if you've seen other videos on the Ciw Python package, we can create this network object using the create network function. And this network we're keeping pretty simple. It's got a single node in it, so we're going to have an arrival distribution, in this case just an exponential with a rate of 1, and a service time distribution with a rate of 2, and the number of servers is going to be 1. Now, instead of passing some of the other routing tools into the routing parameter, instead we're going to pass in process-based, and that's where we provide our function. So, as it says here, a function that returns a predefined route. And other than that, I mean, it's like all the other components with the Ciw interface. It's just a matter of which pieces you plug in at this high level, and it does the rest of the work of making sure that things talk to each other behind the scenes. So we can try running this example. And in this case, I guess I didn't explain what's actually printed here, but here we're getting a set and it contains a tuple of ones. And what that's indicating to us here is that really only the ones were visited, which is to say that this routing behavior is making the customers come back to the same position, the same node again. So that's a pretty simple example. Maybe we should expand out a bit. Actually, let's start another example of, I don't know, complicated process-based. Maybe I shouldn't say complicated. It's not that complicated. Custom process-based routing, let's call it. And we're going to follow an example from the documentation here, and this one we'll type out together. Okay, so let's import, of course, Ciw. Import Ciw, and we're also going to import random. Let's see here. There we are. Okay, and now let's define our routing function. So last time we just had kind of a repeating the same node every time. This time we're going to do something that has some kind of branching behavior, just to show that this function really can be used to make decisions about where an individual goes. So we'll go Ciw.individual to meet their type signature requirements. Simulation is a Ciw simulation. And we won't worry about that. Well, sure. Let's put the return type in. We might as well behave ourselves here. So what is it? It's list of integers. And now, in this example, we're going to branch based on, first and foremost, where the customer is coming from. And we'll do a network this time that has 3 nodes instead of 1, so that it's a bit more interesting than just returning to the same node over and over again. So individuals have a property of what node they actually entered into the system from, where they started. So we can say individual, and we can say starting node. And if, let's in this case say if it equals 1, then we'll have some stuff, and then otherwise, if it does not return, then we'll go int starting node is equal to 2. Then we'll do something else. So let's get into what we should do under these different branches. Now, I think it doesn't know. The LSP may see some warnings or errors because ahead of time it doesn't actually know, and I think this might be kind of patched in the back implementation. So let's go individual ID number. And suppose that, and this to me seems like a very arbitrary rule that you wouldn't actually want for most systems. I'm not sure. I'm not saying you can't have a system like this, but it does seem like a weird example to me. In this case, let's just say, yeah, all ones. Return ones. So what this means is that the trajectory of the sequence is going to be like that repeating one that we saw in the last example, where you go to 1, and then you go to 1, and then you go to 1, and then you're done. You only go through 3 times. And you hit the same node every time. Otherwise, we'll return a different trajectory that starts at node 1 and goes to node 2 and then 3. So that's that trajectory. And then in this one, this branch will go random.random. And if that is, say, less than or equal to 0.5, so a 50-50 kind of coin flip, as it were, then we'll return a shorter one. So they don't all have to be the same length, because these are just different possible sequences of nodes that they could go through that, of course, could have different lengths. So there's a 50-50 chance, if you're starting at node 2, of going through a trajectory where you first go to 2 and then you go to 3. So if you think about this, you could actually expand on this to create probability distributions over trajectories. So it's like predefined, but you could really make this very, very complicated. The major kind of design choice here that has some downsides is that it is all kind of decided completely ahead of time. And so you may not be able to always manipulate this exactly the way that you like, but there's a lot of flexibility here. It's worth knowing this trick. Okay, so then the last, just to make sure we've got a return no matter what here, we'll do 2 and 1. Should be fine. Okay, then we'll do the usual thing that we always do with Ciw, where we're going to define a network. So let's go declare a network, and we'll go Ciw.create network. And let's put in some arrival distributions. So what do we want here? Maybe we will, first of all, just try to be a little organized. So Ciw.dists, and we'll have an exponential with a rate of 1 for the first node, and the second node we'll do a deterministic. And that will have, let's say, a value of 1, meaning it just returns 1 every time for the inter-arrival times. And then the third node, let's say there are no arrivals, so it's none. Now let's go on to service distributions, another little list. Okay. One of the things that gets me with this Kinesis Advantage keyboard is just that the escape key and the tab key are kind of reversed in their vertical arrangement compared to a regular keyboard. So I sometimes hit tab when I mean escape, and I sometimes mean escape when I hit tab. Okay, exponential rate, also 2. Actually, their example says that the other ones are 2 as well. So let's just do that. That seems fine. Okay, and then let's go number of servers. And here we're just going to have straight 1s. And then the last thing, to finally get to putting in our routing behavior. For routing, we'll say Ciw.routing.process based, and we'll pass in our routing function, which here we've also literally called routing function. You don't have to do that, but don't make it a call like my LSP thought I should do. Leave that alone. Okay, and that's defining a simulation. So hopefully that helps you see in a multi-node network as well, which is really what the second example is about, is to say, well, you can start to plan out these different kind of trajectories. Now, actually, we should probably just run it, make sure that, you know, the world works the way we think it does, process-based. And you can always run into spelling issues. Determine, Ciw.dist has no determinist. Oh, ick. There we go. So that runs. So with that, the takeaway is that you can now define predefined paths through your network that a given patient is going to follow, given two pieces of information. One is any properties of that individual themselves, as well as anything that you can get out of the state of the simulation, which is just about everything else, I think. So with that, good luck with your next discrete event simulation project, and all the better if this routing function behavior for process-based. Oh, maybe I should, before I close out, say, like, why is it called process-based? Is really it's this abstraction of saying that there's a process that defines where things should go, like a business process of flow of where things should go. But we won't delve too much further than that in this video. So, like I said, good luck with your next project, and I'll catch you in the next video. Bye.